Welcome, everyone. For today's prep, we're going to continue right on with substitution rule, but this time we're going to look at it for definite integrals. And so by the end of this lesson, well, you'll hopefully be able to calculate a definite integral using substitution rule. And it's going to come down to two methods. So there's two methods we're going to see. Either one, whichever one you want to use is perfectly fine. So whichever one you like better, that's the one you should use. And the difference between the two methods is just how do we handle the limits of integration. So that's the only difference here. The actual finding the antiderivative part, it's going to be basically the same. So the first method is we're going to change our limits of integration. So we know that with substitution, we say we let u equal something, and then we convert all of the variables in our integral from x's into u's. So for method one, we're going to just kind of carry that over into the limits of integration. So we're going to take our limits of integration and convert those as well. And then we just integrate just like we would with regular substitution rule. The second method is we're just going to leave the limits of integration the same. So we're just going to leave them in terms of x and then kind of go through the substitution rule. Now, if we do method two, we have to make sure we convert the antiderivative back to x. So if we don't change the limits of integration, then we have to convert our antiderivative back to x. If we use method one and we change the limits of integration, well, then we don't have to convert the antiderivative back to x. So with method one, there's a little bit more work up front, but then it saves a little bit of work at the end. And then with method two, you kind of get going right away, but then there's a little bit more work at the end. So really, these are equivalent. It's the same amount of work. Just whichever one you like better is the one you should use. So we're going to try some examples, and we're just going to show both methods, and you can decide which one you like better. So let's look at example one, and we're going to do this using the first method, where we actually change the limits of integration. All right, so what do we got here? We got this definite integral. We know it's a definite integral because it has these limits of integration on the integral sign. So we're integrating from 0 to 1. And the function we're integrating here is 2x times x squared plus 1 raised to the power 5. So when we look at this thing, there's quite a bit going on here with our function. And we see that we have some parentheses, and then this power function, and then there's some stuff inside the parentheses. So this is kind of a classic sign. As soon as we see parentheses and there's a whole bunch of stuff inside, and maybe substitution rule. So we're going to kind of approach this just like we would if we're doing an indefinite integral. So the first step is to choose u and calculate du, just like we did before. All right, so what do we get in this case? Well, we're going to let u equal those terms that are inside the parentheses, so all this stuff that's in here. So we're going to let u equal the x squared plus 1. Again, we're just kind of identifying what's going on in the parentheses there. And then once we choose u, we calculate du. So the derivative of x squared plus 1 is 2x. And then we multiply by dx. And we're taking it easy for this first example. So we see that this leftover piece, this 2x, and the dx that we have in our integral here match up nicely with what we just calculated. So we know that we're going to be able to replace this x squared plus 1 with u, kind of by design. And then we're going to be able to replace this 2x dx with du. All right. So how do we handle the limits of integration? So we're going to do this one using method 1. You don't have to remember. We're just calling it method 1. You don't have to remember that the method 1 name doesn't matter. So you don't have to mention that, oh, I'm going to use method 1 for calculating this definite integral. Just matters the work. So what is that? We're going to convert the limits of integration. So now there's a little bit extra work here in step 1. So before we actually get to the limits of integration here, let's actually fill all these pieces in. Let's fill these pieces in. So we're going to take the u equal to x squared plus 1. We're going to fill that in here. And then we'll take and convert our differential as well. All right, so let's see what this is going to look like. So we're going to have u raised to the power 5, because this is becoming u, and it's raised to the power 5. And then the 2x and the dx kind of get swallowed up and become part of our new differential du. All right, so let's worry about the limits of integration. So right now in the original integral, we have 0 and 1, and these are actually in terms of x. So we're going to do one extra thing here, and that is we're going to also convert the limits of integration. So how do we do this? Well, we're going to use our u equation, and we're just going to plug into that. So when you do this, usually helpful, just kind of keep the same structure here that was in the original integral. So x equals 1 is the top limit. X equals 0 is the bottom limit. So we're going to take these two x values and we're going to plug them into our u equation and see what we get. So we're going to plug these into our u equal to x squared plus 1. So you just want to be careful. You want to keep the same upper limit and the same lower limit. So in this case, when I plug x equals 1 in, I get 1 squared plus 1, which is 2. So 2 is going to be my new upper limit. So let's change that over. Boom, 2. All right, now what's our new lower limit? So x equals 0. We're going to plug it into our u equation here, and we get 0 squared plus 1. So our new lower limit is going to be, nope, not 0, 1. So 0 squared plus 1. All right, so now we throw that in up here. And then once we have all this, now we just go through, and this is just a regular definite integral now. So we just do it regular. So really the only thing that changes with definite integral is we have this just little extra step here, but now we're not going to have to convert back to x to get the value. So let's finish this off. So what's the antiderivative? Well, use our power rule. So our variable is u, add 1 to the exponent, bumps us up to 6. Take that new exponent, flip it, put it in front. And then for definite integrals, we put the vertical evaluate line, and nope, we're now in u. So u is equal to 1, u equal to 2. So when we go to do the evaluation for definite integrals, top limit gets plugged in first, bottom limit gets plugged in second, and then we subtract. So we have our 1 over 6. And when you do a definite integral, it helps just kind of set up the framework for what you get when you're going to plug in. So I'm going to plug in my top number here, plug in my bottom number here, and then subtract in the middle. And it helps to get these big parentheses to have your framework all ready to go. So what do we get when we plug in 2? Well, we get 1 over 6 times 2 raised to the power 6. And then when we plug in 1, we're going to get 1 over 6 times 1 to the power 6. And in terms of simplifying this down, I would probably just, well, I might do a little bit extra. The only thing I would simplify maybe is this 1 to the power 6. That's just 1. So we could simplify that down just a little bit. But I wouldn't tire yourself out trying to simplify too much. So there we go. Maybe if you wanted to factor out a 1 over 6. Doesn't matter, though. So that's pretty good. So what did we do here? Well, we kind of started off with our regular substitution rule. So step 1, choose u, calculate du. But now we actually we converted our limits of integration. And then the third step was just evaluate like usual. Now, let's get the antiderivative first. And then step 4 was evaluate. So it's not too bad. We just have to convert the limits of integration. And essentially what we're doing then is we take this complicated definite integral, and by doing the substitution and by converting the limits of integration, we get now just a basic definite integral to do. So we just finished that off just using our regular methods. All right, so in class, we're going to try this method again. We're going to try this example again, but we're going to use the other method just to see how that looks. And then you can decide which one you like better. So we'll kind of save that, and we'll see you in class. Bye-bye.